Okay, ladies and gentlemen, Mr. Barron here with the next set of your flipped classroom notes. And today we're going to be beginning Chapter 5, which is the Thermochemistry chapter. So when you see thermochemistry, that should bring to your mind the idea of heat. And that's what this whole chapter is about, is how heat is involved in different chemical reactions and the transfer of heat, how that can be used in chemistry to find out various different things about the reaction. Okay, so we begin with a definition of energy. This is stuff, those of you who have had some physics experience, you should recognize some of these terms from your physics. Energy is the ability to do work or to transfer heat. And so whenever we use energy to cause an object to move, for example, like if you are pushing something across a floor or lifting something up off of the ground, that is an example of work. And so we don't deal with a whole lot of work in chemistry. Instead, we deal with the other aspect of energy, which is heat. So the energy that's used to cause the temperature of an object to rise is heat. So you can see here there's really two aspects of energy. You have the work aspect and the heat aspect. And this chapter is going to focus on the relationship between the two of those different forms or versions of energy. So first, a discussion of some of the different types of energy. We have potential energy. So potential energy is the energy an object has by its position. So you can see here we have the woman on the bike. She's poised at the top of the hill. So because of that her position, she has potential energy. In chemistry, the potential energy is related to the chemical composition. So the energy in a chemical compound is contained within its bonds. And so there is a potential for those chemical bonds to break, which would then release the energy, changing it from potential to kinetic. So here we can see in the physics example, the kinetic energy comes because as she proceeds down the hill, she has both mass and velocity. So we use the kinetic energy equation, 1/2 the mass times the velocity squared, to find the energy. In chemistry, that energy results from as the bonds are broken. We can calculate how much energy is released during a chemical reaction. And the units for energy that we will use in this class, the SI unit for energy is the joule. The joule. Joule is abbreviated with a capital J. You see there as we break it down into the units, it's one of these what we call a derived unit that is made up of several different other of the more common SI units. So you see that a joule is a kilogram meters squared over seconds squared. So you can see the mass in there with the kilogram, you can see the velocity in there with the meters over seconds, and then the fact that it is squared is how you get your meters and your squared seconds to be squared. Okay, another unit of energy that you may be familiar with from food and things like that is the calorie. So that's not an SI unit, but it is still pretty well used in many areas. And if you wanted to go and relate between the joule and the calorie, you can see the conversion here. 1 calorie is equal to 4.184 joules. And just a side note here, this calorie is not the same as the calories that you would see like on the packages of cookies that you might be eating if you're counting calories. Those are a capital C calorie, which in reality is a kilocalorie. It's 1,000 times bigger than this. So for example, I think like a normal 12-ounce can of soda is like 270 to 300 calories. That would be, in terms of these small C calories, that would be 300,000 of those types of calories. So the food calorie is a capital C calorie, which is really a kilocalorie. All right, as we talk about thermochemistry, we need to define a few things, and one of the things that we need to make you aware of is this idea of the system and the surroundings. So the system is what we want to study. In this case, if we are trying to study these molecules, the hydrogen and the oxygen, the hydrogen being the white molecules and the oxygen being the red molecules here, if we were wanting to study those molecules, they would be considered the system. The surroundings are everything else. So in this case here, the cylinder that they are in, as well as the piston that is involved in this particular apparatus. So energy used to move an object over a distance is work. We mentioned this before. Okay, here's the formula for calculating the work. The work is the force times the distance. So if you know how much force you're applying, multiply it by the distance that the object is moved, you can calculate the work. Okay, but that's not only one way that you can transfer energy. Energy can also be transferred, and this is where it kind of relates more to chemistry, as heat. So in this picture here, you can see a little metal spatula. As the heat is transferred from the Bunsen burner flame to the spatula, you can see that heat because it is glowing red. The metal is getting hotter, it's getting energy. Okay, and heat always flows in one direction, and it always is going to flow from an object that is warmer to an object that is cooler. So an example here is if you are holding a hot cup of cocoa or a hot cup of coffee, the heat is going to be moving from the liquid in the cup into your hands. Your hands are not cooling down the hot cocoa. Your hot cocoa is warming up your hands. And that process will occur until both objects get to the same temperature. So that heat will continue to flow until both your hands and the cup are at the same temperature. Okay, and so energy can be converted from one type to another. Here we see the example of connecting or converting from potential to kinetic energy. Okay, so the cyclist has potential energy at the top of the hill. As she begins to move down the hill, her potential energy is converted into kinetic energy. At the bottom of the hill, all of her potential energy will be converted into kinetic energy, and because she's not any distance off of the ground, she will no longer have potential energy. It will all be transferred into kinetic energy. All right, so this gets into the first law of thermodynamics. This principle also applies in chemistry. And the first law of thermodynamics, simply stated, is that energy is neither created or destroyed. So in other words, what that means is that the total amount of energy in the universe is constant. The amount of energy that the universe began with is the amount of energy the universe has now. The only thing that's occurring is the energy is being converted from one form to another. So if a system is losing energy, that energy must go somewhere. It doesn't just disappear. So if the system loses energy, it must be gained by its surroundings, and vice versa. So if the surroundings are losing energy, then they must be transferring their energy into the system. So whenever we're talking about the energy of a system, it's very, very difficult to calculate the total amount of energy. The total energy in the system is called the internal energy, and it's the sum of all the kinetic and the potential energies of every single component in that system. And we would abbreviate that internal energy with a capital E. And so because it's so difficult to calculate all of the kinetic and the potential energies for every single molecule of substance that's in the system, instead what we refer to more often is the change in the internal energy, which is the delta E. So the Greek symbol delta, whenever you see that, that's always referring to the change. And so you can find that by taking the final energy of the system and subtracting that from the initial energy. So you can see final minus initial gives you the change in the energy. Okay, so a couple of definitions. So if the change in the internal energy is greater than 0, then that means that the final energy of the system is greater than the initial energy of the system. So that means that the system must be absorbing energy from its surroundings. In order for that energy to go up, the energy has to come from somewhere, so it must be coming from the surroundings. And so that type of a change is called an endergonic change. That endergonic change means that it is absorbing energy. Okay, so you can see an example. If you have liquid water, if liquid water is being converted into hydrogen and oxygen gases, the only way that can happen is if it is going to absorb energy. That process, just as a side note, is called hydrolysis. So if you pass an electric current through water, it will start that decomposition reaction and you will get hydrogen and oxygen gases. That's why in the movies, if you see somebody electrocuted, you always see like smoke in that coming off of the water. That is supposed to represent the hydrogen and oxygen gas being formed as the water is hydrolyzed, or as it is decomposed because of the electrical current. Okay, if the internal energy of the system is less than 0, that means that the system is releasing energy to its surroundings. And so that is called an exergonic change. So exergonic refers to energy being released. We'll see in just a couple of slides. You are probably more familiar with the terms endothermic and exothermic. Those are referring to heat. Here they're referring to energy. So the ending part of the word is gonic. Gonic is the Latin word for energy. All right, so whenever energy is exchanged between the systems and the surroundings, that is going to occur as one of the two forms of energy. It's either exchanged as heat, which in thermochemistry is abbreviated with the symbol Q, or as work, which you can see is abbreviated with the W. Okay, so we have our first equation in this chapter. The change in the internal energy is equal to Q plus W, heat plus the work. And so this table is in your book. It's table 5.1. So if the Q is positive, that means that the system is gaining heat. If the Q is negative, that means the system is losing heat. If the W is positive, that means work is being done on the system. And if it is negative, that means work is being done by the system. Or another way to think of that is work is being done by the surroundings. And then finally, for the last one, for the change in internal energy, a positive value means that there is a net gain of energy by the system, and negative means that there is a net loss of energy by the system. Okay, so then whenever the changes of energy are occurring, usually they are accompanied by an exchange of heat between the systems and the surroundings. So these are the terms that you're more familiar with. When heat is absorbed by the system from the surroundings, we call that an endothermic process. So heat is going into the system, that is endothermic. When heat is being released by the system into the surroundings, that process is exothermic. So heat is going out of the system into the surroundings is exothermic. All right, at this point we're going to introduce another definition, the definition of a state function. So usually we have no way of knowing the internal energy of a system, like we mentioned before. Finding that value is simply too complex. You'd have to know the kinetic and the potential energies of all the different molecules in the system. So instead, what we can see very easily is that the internal energy of the system by looking at the temperature. And the internal energy of that system is independent of the path by which the system achieved that state. So in the example here, if we were going to talk about the internal energy of the middle hot plate there, you see you have 50 grams of water that's in the liquid state, and it's at 25 degrees Celsius. So we could find the internal energy of that particular system. But it doesn't matter how that water got to room temperature. It could have gotten from room temperature by starting out as ice that was melted. By heating, we heat up the ice on the hot plate to melt it, or it could have gotten that way by starting out as water that was steam or right at the boiling temperature at 100 degrees Celsius and then cooling it down to get the liquid water at room temperature. Okay, so that means that that is a state function. Okay, so internal energy is a state function. What that basically means is this, is it depends only on the present state of the system, not on the path by which the system arrived at this state. And so the internal energy depends only on the initial and the final energies, not how it got there. Let me give you another example of that I like to use. If I'm going to talk about the elevation of a mountain, let me see how to do this without making shadows. All right, so let's say we have this mountain here. Okay, the elevation, the distance from the base of the mountain to the top of the mountain, that is a state function. Okay, it is a value that does not depend on how I get there. I could start at the bottom of the mountain and I could scale the mountain. I could climb straight up the face of the mountain and get to the top, and my elevation would be one value. I could also start at the bottom of the mountain and I could kind of take a track around the mountain like so. until I get to the top of the mountain. It's going to be a little bit of an easier trek to get there. But when I get to the top of the mountain right here, I'm still the same elevation. Okay, so the elevation of the mountain is a state function. It does not depend on how I get there. Okay, but the distance that I traveled, that is not a state function, because in one case, if I go straight up the mountain, I'm traveling a much shorter distance than if I took the kind of circuitous route around the mountain all the way up to the top. Okay, so the internal energy, delta E, the change in internal energy, that is not a state function. However, the Q and the W are not state functions. Okay, so here we have an example of a battery. So let's say we have a battery that has run out of its energy. Okay, the battery is shorted out, or it's discharged. Okay, so the delta E is the same. It's at 0, but in this case, the Q and the W are different. All right. In the first case, if you have the battery that's shorted out, it didn't do hardly any work. It's a bad battery, it doesn't work right. But if you've ever held onto or tried to feel a battery that has a short circuit into it, it gets extremely, extremely hot. In fact, usually so hot you can't even touch it. It's going to burn your fingers. Okay, so the way that gets to the delta E of 0 is by discharging a large amount of heat. Okay, and the opposite, on the right hand side, here you see the battery that gets discharged because it's causing the fan to work. So it's going to produce a little bit of heat, okay, whenever the fan motor is running. You get a little bit of heat produced, but you also get a lot of work that's done to turn the blades of the fan. So the Q and the W in both of those cases are very, very different, but the energy that's lost by the battery is the same in both cases. So the delta E is a state function, Q and W are not. Okay, the final thing we're going to talk about today is a special type of thermochemistry that's called calorimetry. So because we cannot know the exact energy of the reactants and the products in a chemical reaction, again, that would require measuring the kinetic and the potential energies of all the molecules involved. Instead, we can measure the Q through a process that's called calorimetry. We look at the flow of heat. And usually when we do that, we do it in an apparatus like you see on the left-hand side here. This is called a bomb calorimeter. So you can see basically what you do is you put your sample that's undergoing a chemical reaction into a small container on the inside, okay, and then surrounding that is a larger container that is full of water. And so as the reaction occurs, the water in the secondary chamber is going to either increase or decrease in temperature, and so that can be measured. So as we measure the temperature of the water, we can get an indication of what type of heat transfer is going on by the reaction that's in the bomb chamber. Okay, and so we can use that to calculate two important values that are called the heat capacity and the specific heat. So first, the definition of heat capacity. Heat capacity is the amount of energy that's required to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. Okay, remember those two are proportional to one another, so it doesn't matter if you're talking about Kelvin temperature or Celsius temperature, and that's its heat capacity. All right, so generally you can think of heat capacity as how easy is it for that substance to heat up. So metals have a really high heat capacity. That's why if you're boiling water on the stove and you leave a metal spoon in there for any amount of time, you probably don't want to grab that metal spoon or you're going to burn yourself. However, if you have a wooden spoon in the pot that's boiling, it's not going to absorb heat anywhere near as fast because it has a much lower heat capacity. Okay, the specific heat capacity, or sometimes we just shorten that to specific heat, is the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. Okay, so the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin. Okay, so we can take that then and break that down. So the specific heat, the formula for calculating the specific heat then is the heat that's transferred. So remember, that's our Q value, divided by the mass, multiplied by the change in the temperature. Again, remember, delta means the temperature change. So to find the change in temperature, you would be looking at the final temperature of the substance subtracted from the initial temperature. Or sorry, the other way around. Initial subtracted from the final. So T final minus T initial. Okay, so by carrying out a reaction in an aqueous solution, here we've kind of, and this is something that we will do in a laboratory in this class, is we kind of make our own bomb calorimeter from two styrofoam cups nestled into one another. Okay, we can indirectly measure the heat change for a system by we measure the change in the temperature of the water that's in the calorimeter. So the inside cup is full of water, okay? The outside cup has a chemical reaction going on in it, and so we can measure the temperature using the thermometer. Okay? So the specific heat of water, and in fact the specific heat of any substance is a standard value. It's the same. So the specific heat of water happens to be 4.184, and the units for specific heat are joules per gram Kelvin. And so we can measure the energy change for this reaction by just taking that same specific heat formula and rearranging it. So the energy change, delta E, which is also equal to Q, is equal to the mass times the specific heat of water, 4.184, times the change in the temperature. Okay? So we can carry out a reaction in this particular apparatus, the bomb, and the heat that is absorbed or released by the water is going to be a very good approximation of the enthalpy change for the reaction. Enthalpy, just another word, actually not defined that yet. We'll get into that next time. But it's the internal energy. It's a good approximation of the internal energy change for the reaction. All right. Now, because the volume of the bomb calorimeter is constant, obviously the calorimeter is not going to be changing its volume. That's a metal container. Okay. What we're really measuring is the change in the internal energy, delta E. So as the reaction occurs and you measure the temperature change in the water, that is going to be directly related to the internal energy. So basically what's going on here is there's not going to be any work done. There's no distance. Nothing is moving. There's no force being applied over a certain distance of time. The only thing that's occurring because of the reaction is a change in the temperature of the water. Okay? So for most reactions, the difference is going to be relatively small. Okay. And so this is where we're going to leave off for today with the notes. Also make sure that you watch the second video, which is going to be some example problems. All right, thank you very much.